There we go. So we're talking about the quantum harmonic oscillator, and I said that this was the one of the canonical problems that you would solve to learn about various things. And in this case, we're learning about operator methods. And so we're interested in solving the harmonic oscillator, not by solving a differential equation as you would normally do, but by utilizing operator methods. And in particular, we started off by thinking about the why is this not working? There we go. We started off by thinking about the Hamiltonian for the system. And if we strip away all of the bells and whistles, then the Hamiltonian for the system is basically just a differential operator that's minus the second derivative plus x squared. Okay, it's that x squared part that makes this into the harmonic oscillator. If there was no x squared, this would be a free particle, which we're going to be talking about just now in terms of the continuous and discrete spectra. But for the moment, what we're interested in really is this second derivative operator. Kenisa, question.
So yeah, I tried checking the I don't know if it's called Hamiltonian and the plus one there. I couldn't see where it comes from because I checked. Okay. Yeah.
Okay, so we'll talk about that just now. In fact, I did it in the next slide already. So let me just get there, and then we can talk about it. Okay. So the point is that I have this operator that looks like a squared minus b squared, and the same way you would deal with real numbers in the form a squared minus b squared as a minus b times a plus b, you can factor this Hamiltonian into a plus b times a minus b form. Okay, sorry, there seems to be some decided lag here. Right, so you can factor this into a minus b times a plus b plus some residual thing, which is what Kaniso is asking about now. So let's accept that this is the case, right? Now, here's where I said I covered this already. If I accept that I can factor the Hamiltonian into some operator q dagger times q plus some residual part, then I can write the Hamiltonian as q dagger q plus 1. Okay. Now I want to switch the ordering around. Okay. In this case, I want to ask, what is q dagger? So what is q dagger acting on some test function? So, to understand where the plus 1 is coming from, you have to realize that these are operators, and operators act on test functions, right? And so if I consider, let's say, q dagger acting on the test function psi, right? This is dx plus x acting on dx, minus dx plus x acting on psi. This is the key point here. So minus dx plus x acting on psi is minus the derivative of psi plus x times psi, because x is just a number, right? Are you with me?
Yes.
Good. So now the second operator q acting on this guy is dx acting on this guy, which will give me the second derivative of here, plus dx acting on this thing. But dx is a derivative operator, and it's acting on the product of two things, so I've got to use the product rule. And using the product rule, it first acts on the x to give me just psi. Then it acts on the psi with the x multiplying it. Can you see that?
Yes, yes, yes.
Then there's the x which acts on both of these. X acts on this by multiplying by x, that's this guy, and x acts on this by multiplying it with x, which gives me this x squared factor. You with me?
Yes, yes.
Obviously, this and this are the same, and so they can cancel each other out. And so what's left is this, this, and this, right? Now, in all cases, I have this psi, and I can take the psi out to the right as a common factor. And then I'm left with the second derivative term, that part, the squared term, that part, and here's this 1. This is where the 1 comes in. And it'll come in exactly the same way if I switch the order around. It comes from the product rule.
Yeah, that makes so much sense now. Yeah, that makes so much sense.
Okay. And so what we learned from here is that the Hamiltonian can be written as q dagger q plus 1. But it can also be written as q dagger minus 1. So then I said, okay, suppose I have some eigenfunction. Suppose I have some eigenfunction of this operator q dagger q. We'll call it psi. And this thing has eigenvalue lambda. And crucially, I'm going to assume that lambda is not equal to 0. So non-zero lambda. And then I calculate q dagger q acting on psi by definition is lambda psi. And then I act on both sides of this equation with q. So then that's q times q dagger q acting on psi. And on the right-hand side, it's q acting on lambda psi. But lambda is just a number, right? And in the q dagger q, I can reorganize my brackets so that it brackets out q dagger and then q psi. And then on the right-hand side, I pull out the lambda because it is just a number. And I get lambda q psi. In other words, if I read this as an equation in words, this says that q dagger acting on whatever this guy is, q psi, it's another vector, is just lambda times the vector q psi. In other words, the vector q psi is an eigenfunction of q dagger, also with eigenvalue lambda. So if psi is an eigenfunction of q dagger q, with lambda as its eigenvalue, then q psi is an eigenfunction of q dagger with the same eigenvalue. Except, because this was the caveat that I threw in the first place, except possibly at lambda equals 0. So things could possibly go wrong at lambda equals 0, but for non-zero lambdas, this is true. So then the question that we left off with the last time was, does this q dagger q actually have a 0 mode? In other words, does it have an eigenfunction with eigenvalue lambda equals 0? Because that will be the case, the caveat case that we still need to consider against this statement. Is everybody happy with where we are now?
Yes.
Good. All right. So let's start then with today's lecture, having recapped the last lecture. So the question we left off with is, does this actually have an eigenvalue? So to tell me whether it has an eigenvalue or not, I need to consider the things that this operator acts on. And it turns out that as an operator acting on the set of square integrable functions on the whole real line, q dagger q does indeed have a 0 mode. Okay, so let's pick up where we left off last time. So to see why q dagger q has a 0 mode, again, 0 mode is just jargon for the statement that we have an eigenfunction with eigenvalue 0. So it has a 0 mode for the set of square integrable functions on the real line, on the whole real line. So from minus infinity to infinity, I'm going to consider the following. Let's take the function psi naught of x to be the Gaussian, minus x squared over 2. Okay. Now, this function satisfies, which satisfies the following. Q acting on psi naught is dx acting on psi naught plus x times psi naught, right? Because Q is dx, d sub x plus x, right? D sub x, the derivative of psi naught, if I differentiate this Gaussian, it's just the exponential itself times times the derivative of the argument of the Gaussian, which is just minus x. So that's minus x times psi naught. And then, of course, I have to add this x times psi naught, which is 0. In other words, psi naught, the Gaussian function, is a 0 mode of the operator Q. Well, if it's a 0 mode of the operator Q, and then I act on that from the left with Q dagger, then it necessarily follows that it's also a 0 mode of Q dagger. Q dagger Q. So it's an eigenfunction with eigenvalue 0. Is that clear?
When you said it was the Gaussian function was a 0 mode of Q,
yeah.
Did you say it was also a 0 mode of Q dagger Q?
I said it was a 0 mode of Q, and I showed you just now that it is a 0 mode of Q, right? So if I act on psi naught with Q, I get 0.
Yes.
And 0 is the same as 0 times psi naught.
Okay. Yes.
Okay. Now I have an equation. Q psi naught equals 0 psi naught. Yeah?
Yes. Yes.
I take that equation and I act on that equation from the left with Q dagger. On the left-hand side, I will get Q dagger Q. I will get Q dagger Q times psi naught.
Yes, that makes sense. And then
on the right-hand side, I get Q dagger times 0 psi naught, which is just 0. Are you with me?
Yes.
Which necessarily means that psi naught is also a 0 mode of the operator Q dagger Q.
Yes.
Right. So the operator Q dagger Q does indeed have a 0 mode. Not only that, it's the best 0 mode you could possibly hope for. It's a Gaussian. You can do lots of things with Gaussians. You differentiate it and it just keeps staying a Gaussian. You can integrate it because everybody can do Gaussian integrals, etc., etc., etc. Okay, good. So it has a well-known, well-understood, much beloved 0 mode. How about the operator QQ dagger? So the question we would ask here is, what about the reverse operator, Q dagger? Does it have a 0 mode? My claim is it does not. Why? Let's show why. So the answer to this, I claim, is no. And to see why, note the following. Remember, when I talk about it having a 0 mode, I'm talking about it having a 0 mode of a certain class of functions. In this case, we're asking about square integrable functions on the whole real line. Okay, so if I'm considering the set of square integrable functions on the whole real line, then yes, Q dagger Q has a 0 mode. We've just shown it's a Gaussian, right? If Q dagger, if it does, then it would have to satisfy, then this 0 mode, whatever it is, let's call it, I don't know, phi 1. Let's say this guy is called phi 1. And phi 1 would need to satisfy that Q dagger phi 1 must equal to 0. In the same using the same argument that we just gave for Q dagger Q, right? So if phi 1 is a 0 mode of Q dagger, that means that Q dagger phi 1 must equal to 0. But if Q dagger phi 1 was equal to 0, this means that writing down the full expression for phi 1, which is just a differential equation, I can solve that differential equation, and it will tell me that phi 1 must be e to the plus x squared over 2, just by solving that differential equation for phi dagger, for Q dagger phi. Okay? Does everybody buy that?
Quick question.
Mm-hmm.
Okay, so I get that you get 1 if you're applying the operator Q dagger to the phi 1, but then can't it then happen that Q dagger applied to phi 1 will not necessarily result to the 0, but then after that, once you apply Q to that whole process, then you get the 0 mode? Can't it also happen that way as well? Doesn't necessarily have to be the first operator will give you the 0.
Right, because Q and Q dagger are not independent operators, but they are in fact the adjoints of each other. The answer to your question is no. If I had two independent operators A and B, then I can't necessarily say that AB phi equals 0 necessarily means that B phi equals 0. But Q and Q dagger are not independent operators. They are, in fact, the adjoint of each other. So in this case, no. In this case, if Q dagger phi equals 0, Q dagger phi must equal to 0. And the way to prove this is to actually think about it in terms of the inner product. So I'm going to leave that as an exercise for you to convince yourself, okay?
Okay, thank you.
Yeah, it's a good question though. All right, and the point here is that this guy, e to the plus x squared over 2, is not a square integrable function on the real line. Okay, so Q dagger Q does have a 0 mode. Q dagger does not, if we constrain ourselves to thinking about functions that are square integrable on the real line. So what does this mean? Well, let's go back to the Gaussian, which is a 0 mode of the operator Q dagger Q. Now, since the Hamiltonian can be written as Q dagger Q plus 1 or Q dagger minus 1. And if you think about it, this necessarily means that the commutator of Q and Q dagger is 2. They're the same thing, same statements. Then it follows from that the Hamiltonian acting on psi naught is Q dagger Q plus 1 acting on psi naught, which is Q dagger Q acting on psi naught, but that's 0, plus psi naught. In other words, this is just psi naught. In other words, if the Gaussian function is a 0 mode of Q dagger Q, so it's an eigenfunction with eigenvalue 0 of the operator Q dagger Q, then it necessarily follows that it is an eigenfunction of the Hamiltonian with energy eigenvalue 1 in these normalized units that we're using. Can you see that? This is the crux of this argument, so it's very important that you get this. Everybody with me?
Can you just explain why the energy value is 1? Is it because of the +1 that we got before with the...
Correct.
Okay, thank you.
Okay, so the fact that the energy eigenvalue is 1 comes directly from this statement here. The Schrodinger equation as an operator equation says Hamiltonian acting on wave function is energy times wave function. Okay. And we have just shown that q dagger q acting on psi naught is 0. So h acting on psi naught is q dagger q plus 1 acting on psi naught, which is just 1 times psi naught, which tells me that the eigenvalue is 1 for this eigenfunction. Right. So what? So this means that q dagger acting on psi naught is actually h plus 1 acting on psi naught, which is psi naught plus psi naught, or 2 psi naught. So this Gaussian, which we just guessed as a 0 mode for the operator q dagger q, turns out to not only be a 0 mode of q dagger q, it turns out to be an eigenfunction of the Hamiltonian with eigenvalue 1. It also turns out that it is a eigenfunction of q dagger with eigenvalue 2. Okay, so that's cool. We learned that this guy is actually an eigenfunction of a whole bunch of different operators. Okay, they're all related, so they're not independent operators, but nevertheless, it's still neat. Okay, but it also means that I can do more, and it means that q dagger, it means that q dagger psi naught is an eigenfunction of the operator q dagger q with eigenvalue 2. Why? Because if I operate with q dagger q on q dagger psi naught, this is just q dagger acting on q dagger acting on psi naught, which is just where's q dagger? Q dagger acting on psi naught, we just decided was 2 psi naught. So that's just 2 q dagger psi naught. Okay. And consequently, from here, I can read off that h acting on q dagger psi naught is just q dagger q plus 1 acting on q dagger psi naught, which is just 3 psi naught. Sorry, this is just 3 Q dagger psi naught. So if psi naught is a zero mode of QQ dagger, then psi naught, the Gaussian, is also an eigenstate of the energy of the Hamiltonian with eigenvalue 1. But Q dagger psi naught is also an eigenfunction of the energy operator of the Hamiltonian with eigenfunction with eigenvalue 3, etc. And I can push this argument by recursion, or if you want, you can prove it by induction, that recursively we can deduce that in fact the function psi n, which I'm going to define to be Q dagger to the nth power times this Gaussian wave function psi naught, is, let's make it stronger, must be an eigenfunction of the Hamiltonian and we can even guess what its eigenvalues are. We'll call this lambda n, and lambda n must be 2n plus 1. Okay. And actually, we didn't have to do a hell of a lot of work to make this deduction. So by quick calculation, I'd like you to show this using induction. Any questions? Okay. But we can actually do a little bit more than this even. Because for those of you who've taken at least a first course in quantum mechanics, you will know that the typical solution of the harmonic oscillator, the quantum harmonic oscillator, is stated in terms of Hermit polynomials. Okay, so you write down the differential equation, you recognize that the differential equation can be cast into the form of a Hermit differential equation, and the solution of Hermit differential equations are Hermit polynomials. How do these two things compare, right? So here we've written down a solution of the harmonic oscillator equation in terms of some set of operators acting on a Gaussian wave function. But how does this gel with what you might be familiar with already from quantum mechanics in terms of Hermit polynomials? Well, the answer is that I can write this Q dagger operator, which was minus dx plus x, simply as the product of the minus sign e to the plus x squared over 2, derivative acting on e to the minus x squared over 2. So derivative of e to the minus x squared over 2 multiplied from the left with e to the x squared over 2 multiplied by a minus sign, and you can see that the two sides of this equation will be identical. Well, what this means is that the psi n that we wrote down of x can be written as minus 1 to the n e to the x squared times the nth derivative of e to the minus x squared. Okay, times e to the, sorry, times psi naught. And this thing here is precisely what you would normally call the nth Hermit polynomial, denoted by Hn of x. So that's how these two things tie up together. And the key thing here is that we didn't have to actually solve the Hermit polynomial equation. We were able to deduce it using these operator methods. Any questions? Everybody happy with this? Yes? No?
This all went from 0 to 100 real fast. Just going through the last line again one more time.
All right, let's do that. Very good. Again, is everybody feeling like that?
A little bit.
Good. I mean, not good, but if you are feeling like that, please do stop and ask. I have every intention of making sure that you guys understand what we're doing. You know, I don't have any syllabus that I need to specifically cover with this, but I want to make sure that every step is clear to you. Okay, some steps, there's only so many times I'm going to be able to go through it. I would like you to ponder by yourselves, not necessarily by yourselves. The other thing about my classes is that I strongly encourage collaboration and cooperation in going through lecture notes, in working through the problem sets that I set you. Even though I'm grading them, I want you to cooperate with each other and learn from each other. What you hand in must be your own work, and I reserve the right to ask oral exam type questions on them. That is, I reserve the right to bring them up in the oral exam at the end of the course. But I'm very happy, in fact, I strongly encourage that you talk to each other and collaborate and cooperate. Hand in your own work, but make sure you understand it. Okay, so please do stop me and ask me if it does feel like I've gone from 0 to 100 very fast. So let's go back, let's go over this again. We wrote down the Hamiltonian as Q dagger Q plus 1, which was also the same as QQ dagger minus 1. This is just a statement of the fact that if I calculate the commutator of Q and Q dagger, I get 2. So QQ dagger minus Q dagger Q, that is equal to 2. What does this mean? Well, what this means is that if I act with H on psi naught, and psi naught will always be our Gaussian here, e to the minus x squared over 2. H psi naught is equal to psi naught. Is everybody happy with that part?
Yes.
Good. So what is the implication of that statement? Well, because of this relation, if H psi naught is equal to psi naught, then Q dagger acting on psi naught from here is H plus 1 acting on psi naught. But H psi naught is psi naught. That's what this guy is. And 1 times psi naught is the identity operator acting on psi naught. That's just psi naught. We seem to have got stuck somewhere. Yeah, my screen seems to be frozen. That works. Okay. So that's just 2 psi naught. But if Q dagger Q, if Q dagger Q, sorry, if QQ dagger psi naught is 2 psi naught, this necessarily means that if I act with Q dagger Q on Q dagger psi naught and shift the brackets around, that's the same as Q dagger acting on QQ dagger psi naught. But QQ dagger psi naught is 2 psi naught. So that's Q dagger acting on 2 psi naught. The 2 I can pull out. So that's the 2. What's left is Q dagger psi naught. In other words, QQ dagger acting on Q dagger psi naught is 2 Q dagger psi naught, which means that Q dagger psi naught is an eigenfunction of Q dagger Q with eigenvalue 2. Is everybody with me here?
I'm good.
Good, 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 good. All right, so what is the implication of this statement? Well, this says that if I take this guy, Q dagger psi naught, and I act with H on it, H is Q dagger Q plus 1, as we decided previously, and that is acting on Q dagger psi naught. So that's Q dagger Q, Q dagger psi naught, Q dagger Q, Q dagger psi naught. That was equal to 2 Q dagger psi naught. And then there's another one Q dagger psi naught coming from there. So that's 2 Q dagger psi naught plus another Q dagger psi naught. That gives me a total of 3 Q dagger psi naught. So H Q dagger psi naught is 3 Q dagger psi naught, which means that Q dagger psi naught is an eigenfunction of the Hamiltonian with eigenvalue 3. So let's count our eigenvalues so far. Psi naught is an eigenfunction of the Hamiltonian with eigenvalue 1. Q dagger psi naught is an eigenfunction of the Hamiltonian with eigenvalue 2 times 1 plus 1, which is 3. And so I make a guess and I say that the function psi n is, which I define to be the nth power of Q dagger acting on psi naught. I'm going to make a guess and say that this guy is an eigenfunction of the Hamiltonian, and it will have eigenvalue 2n plus 1. And I ask you to prove that using recursion. Is everybody with me here? Good. So now I want to touch base. So now I've actually solved the problem. Okay, the problem was solve the eigenvalue equation, right? And write down all the eigenfunctions and write down all the eigenvalues. That's what it means to solve the eigenvalue problem, right? If I can write down, no matter how I want to approach it, if I can guess it, if I can solve differential equations, if I can do a bunch of numerics and guess what it comes out of the numerics, I don't care. The point is that I've solved the eigenvalue problem if I write down all the eigenfunctions and the associated eigenvalues. Right? So in linear algebra, you would have had matrices that you would be trying to do this for. Great. Here, it just so happens that our operators are not matrices, they're differential operators, but who cares? The philosophy of the problem is the same. And so the philosophy of the problem is write down all the eigenfunctions, write down all the eigenvalues. If you can do that, you've solved the problem. In this case, the problem is the eigenvalue problem associated to the Schrodinger equation describing the quantum harmonic oscillator. And we have just solved the problem. The eigenfunctions are precisely these psi n's. The eigenvalues are just these odd numbers, 2n plus 1. What we're doing in the next line is saying, but hang on, if I've solved this problem before, if I've encountered this problem before in, let's say, second year quantum mechanics, I would have written down a differential equation. Then I go and look at all the differential equations that I'm familiar with, and I would go, ha, this thing is the Hermit differential equation. It's a particular second order linear differential equation with certain coefficients. We're going to come back to these kinds of equations in a little bit. In fact, in the next section. But I would recognize this just by looking at it hard enough, that this would be the Hermit differential equation. Unfortunately for me, there was some French guy way back when, Hermit, who studied this differential equation, wrote down a set of polynomials that would solve this differential equation, and for his reward, we gave him we call these polynomials after him, the Hermit polynomials. So you spot the Hermit differential equation, like you spot the Legendre differential equation, like you spot the spherical harmonic differential equation, just immediately write down the solution. You can go right down, you can go, find a table of integrals of solutions of differential equations, and they will have them. So you go, Hermit differential equation has solution, Hermit polynomials. The Hermit polynomials all take this form here. So the question is, how do you get to this form from this form? And the answer is by staring at this guy, Q dagger, which is minus dx plus x, minus d by dx plus x. And you can recognize that since we're working with Gaussians, this thing can be written as minus e to the plus x squared times the derivative with respect to x of the Gaussian. You can just do the calculation and you'll see that if you do this calculation, you will get nothing but minus dx plus x, which is what we were calling Q dagger. So then you take this Q dagger, you stick it into here, and you find that you take the nth power, and it comes out to be exactly this. You should definitely do that exercise and convince yourself that it comes out. So this object here is precisely the nth Hermit polynomial. So that's all I was doing, was touching base with what you might already be familiar with from quantum mechanics. Is that a little bit more clear?
Yeah, that's 100% clear now. Thank you so much.
Good. So, it might occur to you that this is a trick, okay? And it's a trick that relied on us being able to take the second order differential operator and break it up into a product of two first order operators. Well, it turns out that a surprising number of differential equations that you would encounter in mathematical physics satisfy this property. Now, second order differential operators are rife in mathematical physics. The wave equation, the heat equation are all of the form second order differential operator. Okay, Schrodinger's equation is effectively what we're working with here. All second order differential operators. And the technique that I've just described to you, where I take a second order differential operator and pull it apart into a product of first order differential operators, possibly plus some residual thing there, applies very generally for these kinds of operators. So whenever I can take a second order differential operator, pull it apart into first order operators, I can always pose my problem as an eigenvalue problem for which interchanging the order of the operators, Q dagger Q, Q, Q dagger, will lead me to solve the problem in this way. And even though this, this sounds like a sneaky trick for solving a particular differential equation, it turns out that these techniques are very useful for any second order factorizable operators. In fact, the whole field of what we would call supersymmetric quantum mechanics is built on this premise that I can factorize my differential operator into a set of what are effectively called supercharge operators. Okay? So I want to do one quick example just to finish up this lecture. And unfortunately, I planned to cover more, but I don't mind because we've elaborated on some points. So the question I would like to start this next thing by asking. I should ask your permission. Can I go over by about 5 minutes? Is that okay with everybody?
Yeah, for me it's okay.
Okay, good. Good. Go. If not, of course, the lecture is recorded, and I'll just go over a little bit, and then I'll store the recording, and you're welcome to leave if you have somewhere else to be, and I'll put it up on either the Vula page or the YouTube channel. So the question I would like to ask here is, what about continuous spectra? So far, we've been talking about discrete spectra. That's why we had this label n. It was a discrete label. It was an integer. We were counting n that way. But what about if sigma of my operator, let's say t, is continuous? Well, to see how this works in this case, let's consider the simplest example I can think of, simplest physical example I can think of, which is a free particle on a real line. So this is just a particle which doesn't move in any potential. It's moving on the real line. It can move left. It can move right. If I push it, it'll just keep going by Newton's third law, and there's no potential involved in this. So the Hamiltonian for a free particle on the real line, R, is simply h equal to minus dx squared. Okay. And it acts on functions in the interval from, let's say, minus L over 2 to L over 2, with L eventually taken to infinity. Right? So what we do is, in order to make sure that our integrals converge and all of that, whenever we need to take integrals, we'll put a bound on the interval that we're considering. So instead of considering the whole real line, we'll consider the interval from minus L over 2 to plus L over 2, and then at the end of the day, we can just send L to infinity. Right? The eigenfunctions here of this operator are the functions, let's say, phi k of x equal to e to the I k x. I haven't put any bounds on k. And since h acting on these phi k of x's is minus dx squared acting on e to the I k x, each derivative pulls down a factor of I k. So this just gives me a minus k squared, which cancels with the minus sign there. And I get k squared phi k of x. In other words, the eigenfunctions are these e to the I k x's with eigenvalues lambda equal to k squared. Okay. That's really all I wanted to do today. But let's talk through this particular statement here. The eigenfunctions for a free particle moving on the real line are nothing but what physicists would call plane waves, right? E to the I kx is sine kx plus, cos kx plus I sine kx. So these are plane wave solutions, right? These plane waves are the eigenfunctions of the operator minus dx squared. with eigenvalue k squared. Next time, we're going to follow up on this and show what the effect of imposing boundary conditions on this problem are. So what we'll do in particular is we'll take this real line and we'll identify the real line. So we'll compactify it on a circle, and then we'll consider a particle on a circle. We'll show what that does to the eigenfunctions. We'll write down some normalized eigenfunctions. And we'll talk about what I call density of states. Okay, so that'll take us to more or less the end of this section, and then we'll use what we're building on here to revisit differential equations and their solutions. And we'll revisit it in a way that I think you should be familiar with, and this is the method of, well, this would be the analog of the method of Frobenius's power series expansion for differential equations. So we're going to be applying it to complex differential equations. So that's what's coming up in the next lecture, which will be on Tuesday. Any questions?